Welcome to today's webinar, Enabling 3D Coupled Battery Simulation with CONVERGE CFD software, brought to you by Convergent Science. Thank you for joining us today for the third installment of the 2024 CONVERGE webinar series. My name is Mattias Sulis, and I am part of the business development team at Convergent Science. I will be your host for today's event. I'm glad I can be here with you today and learn from my colleague Kislaya about battery 3D CFD modeling using Converge. Convergent Science is a rapidly growing computational fluid dynamics software company. Our flagship product, Converge, is an industry-leading CFD solver used around the globe to simulate fluid flows in complex systems. Converge features truly autonomous meshing, which eliminates all user meshing time and helps provide fast, accurate results for our clients. Now it is time to introduce our speaker for today's event, Kislaya Srivastava. Kislaya is currently a principal research engineer at Convergent Science in Northville, Michigan. He earned his Master of Science from the University of Michigan, Ann Arbor, in mechanical engineering, specializing in thermal and fluid science. He has 7 years of industry experience applying computational fluid dynamics and other numerical tools to simulate and analyze a wide variety of complex fluid flow and heat transfer problems. During today's webinar, if you have a question for Kislaya or the team at Convergent Science, please use the question box on the GoToWebinar toolbox. Questions submitted during the webinar will be answered at the end. Without any further delay, I will now pass the ball to Kislaya. Thank you all.
Thank you, Mattia. Let's get started with today's webinar. So CONVERGE CFD software is well suited for battery simulations that can involve complex 3D flows and associated heat transfer. These geometries for batteries and battery pack systems in general typically tend to be very complex and complicated. And as Mattia mentioned, Converge's autonomous mesh generation capabilities will mesh the domain during runtime by the solver and thereby reducing user effort and reducing users' total time to solution. Converge CFD software can also be used to model chemistry in complex geometries. As such, Converge contains the SAGE detailed chemical kinetic solver, which is an established solver used for a wide variety of combustion applications, from IC engine combustions like premix, non-premix regimes, to rockets, to burners, to oil and gas industries, and also after-treatment chemistry. So thermal runaway can be thought of as battery combustion. So a lot of the expertise we have modeling gas-phase chemistry can be easily applied to model battery vent gas combustion chemistry in the gas domain, but also the thermal runaway chemistry or thermal runaway heat release chemistry occurring inside the solid. Converge also contains adaptive mesh refinement approaches that allows you to automatically resolve important flow structures and only add refinement where most needed. This allows you, for battery thermal runaway problems, for example, capture the diffusion of vent gases within the battery pack, capture the flame front during battery pack fires, and also capture a thermal runaway propagation front inside the solid at relatively low computational expense. A wide variety of other physics-based 3D modeling capabilities have routinely been employed for complex battery simulations. Some of those capabilities have been listed here. The user will start off with the import of his battery pack system geometry, and users can import native CAD formats and start to construct a model without having to worry about creating a mesh, which is taken care of automatically by the solver. Battery simulations within Converge are typically 3D conjugate heat transfer simulations, whereby you model both the fluid and the solid domain in the same simulation, and their temperature solution is coupled at interfaces. For 3D CHD simulations, appropriate solid thermal properties are included. If you're looking at steady-state temperature solutions for battery systems, we make use of the supercycling approach that accelerates these steady-state solutions for solids. Innovative cooling designs like air-cooled, liquid-cooled batteries can be investigated using the 3D CHD modeling capabilities, And also new cooling designs like immersion or impingement cooling can also be included or investigated using Converge. Such cooling designs can also involve multi-phase simulations, which can be easily handled using our volume of fluid or VF modeling capabilities. To model complex turbulent flows, Converge allows you to select from different RANS, LES, and DS turbulence models based on your requirement. If the batteries become too hot, especially during the thermal runaway event, radiative heat transfer can also be included in your simulations using a variety of radiation modeling techniques available within Converge. Converge can also model fluid structure interaction simulations, and for more detailed simulations, including deformations, we can apply a co-simulation Abaqus coupling approach, for example, modeling battery swelling. Now, batteries generate heat during their normal operating conditions, so appropriate heat source must be enabled in your simulation. You can use experimental data to specify a heat source, which can be non-uniform, or Converge also contains the equivalent circuit model and the electric potential solver, which will allow you to evaluate an electrothermal response. Converge also has the ability to directly couple an interface with GT Suite and GT Autoline 3D, whereby you might construct a system-level model for your battery pack, but calculate or evaluate detailed flow simulations using Converge. To model the complex problem of battery thermal runaway, we make use of the SAGE detailed chemistry solver. We model the thermal runaway reaction rates occurring inside the solid, and also the vent gas combustion reaction rates occurring in the fluid domain. More physics can be included in your battery simulations. For example, you can make use of the Lagrangian particle modeling approaches to model liquid electrolyte or solid particulate matter being ejected from the battery during the thermal runaway event. Our users often make use of user-defined functions or UDFs to code in their own custom and innovative battery models and have them interface with a regular Converge simulation. We'll start off with a discussion on some typical battery thermal management simulations that we have done using Converge. Shown here on the left is an example of an air-cooled battery pack. This is an e-bike battery pack made up of 40 cylindrical cells, and the working or the coolant fluid is air. As you can see, we conduct a detailed 3D CHT simulation looking at steady-state temperature distributions in your battery solid. Due to the ineffective cooling design for this battery pack, you can clearly see that some of the batteries have reached temperatures of around 360 Kelvin, and they are now at risk of going into thermal runaway as self-heating reactions have started to kick in. On the right-hand side, we look at a design for a pouch cell with liquid cooling channels. And now you can study a 3D distribution of temperatures within your battery solid and ensure that your cooling design ensures that the temperatures, the 3D temperatures or the temperature differences are within a normal operating temperature range for your particular battery. Now, in order to evaluate your thermal management cooling design, you want to ensure that you correctly model or simulate the heat generation occurring inside the battery. You could use predictive models to evaluate or include heat generation during the simulation inside your battery solid. One of the models we have for battery heat source is the battery equivalent circuit model, or the BEC model. This is a lump parameter model that allows you to evaluate for an electrothermal response. In this model, we represent the battery as an electrical network with a series of resistance-capacitance pairs. This is a simplistic and a computationally inexpensive model and is very popular with battery simulation engineers. The inputs required for this model are as follows. You require a current profile, and this current profile could mimic, like, let's say, a typical drive cycle for your, or a discharge cycle for your particular battery at hand. You also require some data for that particular battery you have represented as an electric circuit. You require data for open circuit voltage for your particular battery, varying with state of charge. And depending on the number of RC pairs you have selected, that allows you to obtain a nonlinear response. you are required to arrive at values for, or enable or input values for resistance and capacitance for each RC pair. These inputs or these battery data tables are obtained from closely controlled experiments for that particular battery. As such, it is an empirical model. You can switch between different current rate profiles and evaluate the voltage response and the heat release rate inside the battery. But if you switch your battery type itself, then you'll have to recalibrate these model input parameters. CONVERGE use the following equations to calculate a nonlinear terminal voltage response, which will be translated to a heat source term that is fed uniformly into the battery solid. Now your battery temperatures can rise, and you can do a CHD simulation to evaluate your cooling design. Here's a quick example of a plug-in hybrid electric vehicle battery pack module warm-up simulation. This is a liquid-solid CHD simulation of 24 pouch cells in this module with liquid cooling fins with liquid cooling channels running inside them between a pair of pouch cells. This is a fully transient simulation run for 10 minutes of simulation time. The equivalent circuit model generates heat within each pouch cells, and we have enabled the equivalent circuit model to operate under 3C charge-discharge cycle for this particular pouch cell. We also enabled ohmic heat generation for the tabs and bus bar. Since these simulations are required to be run for long physical durations, we employ acceleration techniques like the fixed flow techniques to speed up these simulations. And as such, you can evaluate for a 3D temperature distribution inside the battery and effectiveness of your particular cooling design. CONVERGE has also been used to model new approaches to battery cooling. Something that's becoming popular in the industry is phase change materials, which is a passive cooling approach. The phase change material is a heat storage device. It absorbs heat during melting and releases heat during solidification, as such, acting as temperature regulators for that battery. As the battery heats up, the adjacent phase change material that surrounds the battery heats up along with it, and at a particular temperature range based on the material, it melts, absorbs heat, and regulates the temperature or fixes the temperature of that battery. This is becoming popular as it is a lightweight, compact, efficient, consistent, and sustainable method of battery cooling, and also versatile depending upon your selection of phase change materials. To model the phase change process of such materials, we make use of the solidification and melting model. And this is done using the enthalpy porosity method. At that particular melting temperature ranges, the material will change phase from solid to liquid or vice versa. A porosity value of 1 implies the material is fully solid. A porosity value of 0 implies the material is fully melted or fully liquid. And any value in between is a mushy porous zone. In these simulations, liquid flow is enabled, modeled as laminar and incompressible. There's no strong turbulent effects for this particular case. It's a slow process. We also include the Boussinesq approximation to model buoyancy effects and natural convection, which in the coming slides you will find is important to capture. Again, these are transient 3D CHD simulations with the solid and the fluid domain for the melted liquid. Looking at the results for such simulations for phase change materials, again, we took an 18650 battery in orange, and it is surrounded by this blue phase change material. The phase change material selection depends on the ideal operating temperature range for your particular battery. We want this battery to operate somewhere in between 314 to 317 Kelvin, which is an optimal operating temperature range. As such, a selection was made for paraffin wax, which is a standard phase change material. If you run this simulation, you can see that the battery warms up. We have enabled a quick discharge cycle for this particular battery that starts to heat up using the equivalent circuit model, and in the vicinity, as the temperature rises, the phase change material starts to melt and starts to absorb heat. And you can see with the simulation with phase change material, the temperatures are starting to flatline at that particular range, 314 to 317 Kelvin. Now, you might notice that the temperatures with and without phase change material deviate right away. So it's not a an apples to apples comparison because of the extra thermal mass due to the phase change material. So a much fairer comparison would be to look at a simulation where the phase change material has no latent heat capacity. It cannot absorb heat during melting. If that's the case, you would see that the temperature keeps on rising within the battery. But due to the latent heat capacity, the temperature is now stabilized or regulated. And that sort of showcases the temperature regulation effect of phase change materials. Now you can do more detailed evaluations of phase change materials. You can look at the temperature distribution within phase change material. You can make a careful selection of phase change materials depending on the operating temperature range you require. You can improve your design, but also phase change materials can also heat up the solid when the temperatures drop, as shown here. When the battery starts to operate under low current, low C profiles, or under low ambient conditions, you will see that the melted liquid now resolidifies, releases heat, and continues to regulate the temperature of the battery, thus ensuring optimal performance for that particular battery at that optimal temperature range. Now, you might look at that problem and say, well, that seems like a purely conduction-driven problem. Why do I even need a CFD solver for this particular problem? Well, due to the timescales for that particular problem run for thousands of seconds or minutes or hours of simulation time, you have enough time for the natural convection currents to be set up within the melted liquid, as you can clearly see occurring here. The melted liquid starts to rise up due to buoyancy effects, and that's why capturing natural convection or buoyancy effects is important for this problem. This leads to non-uniform consumption of phase change material and non-uniform temperature distributions in the battery, which is important for engineers to consider when they start to design such cooling systems, especially for large systems. You want to make sure that the phase change material is being effectively or efficiently utilized. So you not only have conduction heat transfer here to the phase change material, but around the melted liquid which surrounds the battery, there's also convection currents being set up, and now you have an associated convective heat transfer, which is important to include. So based on this understanding of the behavior of melted phase change liquid and the natural convection currents that can be set up, we seek out to showcase how we can use 3D CFD solutions using CONVERGE CFD to better model phase change material matrices or phase change material designs. One drawback of phase change material is that they have low conductivity. So once the liquid melts around the battery, it acts like an insulator. To improve that, people often include, or engineers often include, metallic fins to improve conductivity. Now you can take advantage of the flow currents that are being set up and seek to improve these metallic fin designs, which is what we did and showcased at the 2023 NASA Aerospace Battery Workshop. We adopted a helical fin approach, or a helical fin design, that took advantage of these natural convection currents and flow along these helical designs, or better flow along these helical designs. You can clearly see that a simulation run without flow gives much higher temperature predictions for the battery and lower heat transfer rates. But by enabling flow in our simulations using CONVERGE CFD, you can see that you get enhanced heat transfer due to convection and more realistic predictions for battery temperatures. And then you can further arrive at better designs for these metallic fins. Here we employed a double helical design where we sought to change the flow direction of the melted liquid in order to consume the unmelted or the solid phase change material, based on our understanding on the performance of previous designs. As you can clearly see, there's some unused phase change material here. Now, the equivalent circuit model is a lumped parameter model. The heat source is released uniformly within the battery, but there are some 3D effects you want to take into account. One of those 3D effects is short circuits, internal short circuits that can occur at local areas of the battery and release heat locally. So we have augmented the equivalent circuit model with a short circuit network. The short circuit network can be triggered at user specified times or temperatures. And when you enable short circuit, you see, depending on the short circuit resistance you have selected, you get a sharp decay in state of charge. So internally, there's a short circuit event and all of the electrical energy is released. The heat release associated with short circuit, which is the short circuit current square times the resistance of the short circuit, is released only around a local volume, shown here around the cylindrical volume, which can represent a nail penetration event. So now you get sort of local 3D effects you are able to capture. You have a local temperature rise due to internal short circuit, and you can use this model to trigger thermal runaway mechanisms, which we will discuss shortly. But when you switch over to higher energy density batteries like pouch cells, it's not just short circuit that is 3D and non-uniform. The regular heating itself can be non-uniform. As you can see in experimental IR images, the heating is stronger near the tabs where the current density is expected to be higher. Such non-uniform heating can be included through using experiment data in CONVERGE, and you can evaluate sort of complex 3D behavior or non-uniform behavior for your phase change material melting. But in order to conduct predictive simulations for non-uniform heating, we have enabled the coupled electric potential solver within CONVERGE. This allows you to perform a 3D analysis for a voltage distribution and a current distribution inside the battery. Within the battery, we solve for two potentials, a cathode potential Phi1 and an anode potential Phi2. Appropriate boundary conditions for those two potentials are set. So we have setting 4.5 volts on the positive terminal and 0 volts on the negative terminal. And we solve for these two potential equations coupled with the source term. The source term is calculated using an electrochemical model. When you get a potential distribution, you can convert that to an electric field distribution, electric current density distribution, and that is again translated to a heat generation term, ohmic heat generation due to the flow of current, and also includes the electrochemical heat release depending on the selection of an electrochemical model. So now you get non-uniform or 3D behavior of potential distribution, 3D behavior of current distribution, and heat generation. This can allow engineers to better analyze the electrothermal behavior for that particular battery. In this pouch cell design, both tabs were on the same face. So you have high current density on the top face, so you get more heat release on the top face. So you're going to get higher temperatures on the top face than the bottom face. You're also going to get sharper state of charge drop on the top half of the battery than the bottom half. So the battery is inefficiently operated or consumed. So this can allow engineers to investigate better designs for pouch cells. For example, an opposed tab design will ensure that the heat generation is more uniform inside the battery and the temperatures are more uniform and the battery ages uniformly as opposed to non-uniformly in the previous designs. With the coupled electric potential solver, we include the single particle model, which evaluates for electrochemistry within your battery solid. And that is just done only inside the battery solid, not the tabs. So using the single particle model in these results here shown on the left, we predict a voltage decay over the operating time for that particular battery and compare it to the experimental or published data. Looking at 3D results, the electrochemical model is implemented in 3D and takes into account local conditions. So it takes into account the local temperatures and the local state of charge across that battery. So the current generation, as you can see, is higher across near the tabs, higher negative value because this is under a discharge scenario. The positive or negative sign just depends on your sign convention for charge or discharge. You see more current being generated near the tabs and less current being generated bottom. And the electrochemical model also evaluates the electrochemical heat release term, which is stronger on the top half of the battery. So such 3D effects, such 3D electrochemical effects can also be included in CONVERGE simulations. CONVERGE can also easily couple with GT Suite and GT Autoline 3D. in order to evaluate wall boundary thermal effects and conduct CHT simulations for battery packs. In this CHT coupling approach, the fluid is solved within converge. You solve the complex turbulent airflow within converge and associated heat transfer, convective heat transfer. Those heat transfer coefficients are provided to the GT suite model, which can be a system level model for the entire battery pack. Those HTCs are mapped onto the GT solids, and the GT model will solve for solid temperatures. You can also take advantage and make converge directly coupled with GT Autoline 3D that contains a wide variety of electrochemical models for different batteries. The updated temperatures of the solids and the batteries are fed back to converge, and a new time step is solved for converge to get updated values for HECs. This is the code simulation option, so both codes are run at the same time and exchange information at every time step. So looking at results for that particular simulation, here you look at flow results. In the converge simulation, the boundary temperature, 3D boundary temperature distribution, however, comes from the GT suite simulation that solves for temperature distribution in the casing and also in the pouch cell. Within the pouch cell, Autoline 3D evaluates for electrochemical reactions, reversible reactions, and so forth. Now we switch our attention to the more complex problem of battery thermal runaway that we solve using the SAGE detailed chemistry solver, and we solve it in 3D to get more accurate results. To employ the SAGE detailed chemistry solver for battery thermal runaway, we make use of established thermal runaway mechanisms that evaluate for reaction rates and heat release rates within the solid. In this particular example, we are seeking to model thermal runaway initiation and propagation within a prismatic lithium cobalt oxide type battery. The nail penetration event causes a local short circuit. The local short circuit will release heat, and temperature in the vicinity of the nail will start to increase. And as temperature rises based on local conditions, the reaction rates will increase, and soon you will have a sharp thermal runaway propagating inside this particular battery. The results from our simulation have been compared to published results, and using the SAGE detailed chemistry solver, you see that the simulations are very quick within converge. If I pause the animations here, you can clearly see we also take advantage of adaptive mesh refinement based on temperature to follow and closely track the thermal runaway propagation front inside the battery. And this is vital to capture the correct thermal runaway propagation times and heat release. Looking further at these thermal runaway reaction mechanisms available in converge, currently we have two established thermal runaway mechanisms users can directly select from. We have the Hatchard-Kim thermal runaway mechanism, which was established for an lithium cobalt oxide battery chemistry and consists of 4 reactions. We also have the Wren mechanism, which was created for an NMC or a nickel manganese cobalt battery chemistry and consists of 6 reactions. If you look at these reactions, they are as follows. We have a reaction rate that models SEI decomposition. We have one that models reaction between the anode and the electrolyte. We have one that models reaction between the cathode and the electrolyte. And then we have one that models the electrolyte decomposition process. The Wren mechanism has some extra binder-related reaction rates. If you look at the format of these reaction rates, they're very similar to the Arrhenius format we typically come across for fuel oxidation problems. So a lot of the expertise we have modeling gas-phase chemistry with the SAGE detailed chemistry solver can easily be applied to model the thermal runaway chemistry accurately. Now, users are free to select between these two mechanisms, and users have the flexibility to change these reaction parameters, like the pre-exponential term and the activation energy and so forth. These reaction rates take into account local conditions, so local temperatures, temperature at each computational cell, and also the species concentration at each computational cell. But if you have your own custom thermal runaway mechanism for a new battery type or an innovative battery type, or an updated thermal runaway mechanism, then you're always free to code that up through a simple UDF approach. We have default UDF frameworks that we can forward to a user so they can code in their own custom thermal runaway mechanisms. Selection of suitable thermal runaway mechanisms is vital if you want to reproduce the actual experimental behavior of your battery. As you can see here, different batteries or different battery chemistries behave differently. They have different thermal runaway behavior. Some batteries are more safer than others. It's not just chemistry that differs. Thermal runaway behavior can also differ within the same chemistry. NMC can be made up of different NMC cathodes, NMC 333 or 811, 622, etc., depending on relative composition of nickel, manganese, and cobalt. They'll all have different thermal runaway behavior. It can also differ between different manufacturers due to some manufacturing realities. So if you just switch between different thermal runaway reaction mechanisms, you will see that you will get very different thermal runaway behavior for the same problem. If you slightly change the thermal runaway reaction parameters, you will see similar differences. So an approach we recommend to our clients is to take experimental data for their particular battery, closely control calorimetry data for single cell tests, identify key indicators for thermal runaway, and calibrate our default thermal runaway models. As I said, users have the flexibility to change these thermal runaway reaction parameters. Of course, you can always use UDF to code in your own custom thermal runaway mechanism that you find suitable for this particular battery type. Now, to note here, if you look at these reactions, thermal runaway reactions, you just have 4 to 6 or 8 reactions as best. The SAGE detailed chemistry solver has been used for more detailed reaction mechanisms, like thousands of reactions with thousands of species for fuel oxidation or fuel combustion problems. So it's very easy for SAGE to handle these reaction mechanisms, but at this point, they are not species-based. You don't need to take into account the actual lithium species, the nickel species, manganese species, cobalt species, etc. That's an area still relatively new and under study, and we're happy to work with our clients, both academic and industry clients, to arrive at more detailed reaction mechanisms to model thermal runaway and take into account species composition. Convergent Science is dedicated to widespread improvements in chemistry modeling approaches. That includes battery thermal runaway chemistry. And we seek to arrive at a comprehensive species-based reaction mechanism for thermal runaway chemistry as part of the Computational Chemistry Consortium, which brings together industry, academic, and government partners to develop detailed chemistry reaction mechanisms and also validate them with experimental data. To assist with thermal runaway calibration, we do have optimization utilities that will allow you to tune the parameters of the thermal runaway reaction mechanisms to minimize the error with respect to experimental data. Here we calibrated the two-step thermal runaway reaction mechanism. The original mechanism in green was severely over-predicting thermal runaway behavior, but the optimized mechanism now reproduces experimental behavior. We also have a more detailed thermal runaway mechanism generation tool, which allows users to create their own custom mechanisms from scratch and create any number of reactions for their full thermal runaway mechanism. This takes DSC data, differential scanning calorimetry data for individual materials. So here I'm showing DSC data for just cathode. So we're trying to create a cathode reaction rate using this data. So using the DSC data fit tool, which can be found in Converge Studio in the chemistry modules panel, users will feed in the experimental data to this tool, and users will select a reaction format. So this is not just a simple curve fitting exercise. You can include some physics into this reaction modeling technique. As seen here, this reaction equation is an equation format proposed for solid decomposition processes, which is what the cathode decomposition is. And it's made up of 3 stages, which mimics 3 crystal structure phase change processes within the cathode decomposition. So we're including physics in our simulation, and then the tool will arrive at calibrated values for reaction parameters for particular for the cathode chemistry. So you can do this for cathode reactions, you can do it for anode, electrolyte, etc., and get a complete reaction mechanism. The approach to calibrate simulation reaction mechanisms to experimental data and use them in converged simulations was showcased by engineers from IFPM at our 2022 Converge User Conference. They started out with a heat wave search test for their pouch cell. They got their experimental data from those closely controlled tests. They used the Hatchard-Kim mechanism and calibrated those reaction parameters to match the experimental data, and then applied the calibrated mechanism or the tuned mechanism to your converged simulation. So you can clearly see now that the converged simulation with the calibrated mechanism matches well with the experimental data, while the original Hatchard-Kim mechanism did not predict the thermal runaway behavior correctly. Once you have a calibrated mechanism, you can switch over to more larger problems modeling cell-to-cell thermal runaway propagation within battery packs. In the previous showcase air-cooled battery pack, we selected 4 cells to go into thermal runaway, triggering them using an overcharging scenario. So those cells will go into thermal runaway very quickly, and then heat is conducted, convected, and radiated to the surroundings, and soon you'll have a cascading thermal runaway propagation across the entire battery pack. And all of this is solved for in 3D. For this particular problem, conduction was the most dominant pathway for thermal runaway propagation. A similar study for a larger problem, the plug-in hybrid electric vehicle battery pack module, we selected one of the cells in the middle and initiated a short circuit in those cells, and we tried to investigate how long it takes for thermal runaway to propagate across the entire battery pack and across the cooling fins, and then you can investigate better cooling or thermal runaway mitigation designs. If I pause the animations here, you can still see that thermal runaway is being solved in 3D with the inclusion of AMR for optimal runtimes. Another example for battery pack thermal runaway propagation studies is the work we did in partnership with Renault. So engineers at Renault wanted to investigate what would happen to thermal runaway propagation if they changed the compression pad thickness. So we developed a methodology to investigate this. Again, we started off with single cell experiments, got experimental data, and calibrated the mechanism, and then we switched over to a pack level simulation. So this Renault pack, we trigger cell 8 in the center, and then we seek to study thermal runaway propagation to adjacent cells and also across these compression pads which are placed in between a group of 4 cells. Looking at the results for these simulations, you see we triggered the cell 8 and it easily propagates to these cells 7, 6, and 5, but across the compression pad, it takes a while for it to propagate to cell 9. Now, what would happen if the compression pad thickness was changed? If we change the compression pad thickness by half, you will see that the cells on this direction, where there's no compression pad, it doesn't affect their thermal runaway propagation behavior. But for cell 9, between which there is a compression pad, you will see now thermal runaway is propagating much more quickly and much more strongly. So engineers can perform such simulations using CONVERGE CFD, get a predictive analysis for thermal runaway propagation behavior, and understand thermal runaway propagation behavior to design their systems, taking both into account thermal runaway propagation times, but also the size of the battery pack and the weight of the battery pack, which depends on the compression pad thickness. Again, a quick example of why you want to run these simulations in 3D. Thermal runaway inherently is a 3D process, but there are some 3D effects that come into play which can significantly affect your thermal runaway propagation times for such simulations. In this simulation, we seek to initiate thermal runaway in cell 3 and understand how long it takes for thermal runaway to propagate from cell 3 to cell 4 across this cooling fin. We triggered this thermal runaway in cell 3 using a short circuit source, a local short circuit source. But we found that if we place the short circuit source near the cooling design or the cooling pathways for this cooling fin, we saw a delay of around 15 to 20 seconds for position 1 for cell 4 to go to thermal runaway, shown in red. But if we place a short circuit event in some sort of a blind spot to this cooling design, You see there's only a delay of around 5 seconds for thermal runaway to go into cell 4. And such 3D effects are important to consider because you can never know in reality where the short circuit is going to go. So by better understanding these 3D effects, you can accurately model thermal runaway propagation behavior and start to investigate thermal runaway mitigation design strategies. For some battery packs, radiation can play an important role, especially for cylindrical battery packs where you have a fluid domain in the middle. So you want to include radiative heat transfer and see its influence in the thermal runaway propagation event. For this particular example, we made use of a discrete ordinate finite volume based radiation model that solves for a radiation transport equation to include radiative heat transfer. And then we found that with radiation, we got faster thermal runaway propagation within the entire battery pack. So CONVERGE is able to handle all forms of heat transfer, conduction, convection, radiation, but you can make a selection on whether radiation is important or not for your particular case. Now, thermal runaway not just involves heat release rate, but also involves venting of gases. So in the 2020 NASA battery workshop, we showed our case studies where we conducted detailed simulations of vent gas distributions from the thermal runaway battery within the battery pack. These vent gases comprise of hydrocarbons like methane and some hydrogen, which burns very well. And these gases only burn when the upper and lower flammability limits or criteria are reached. So using such detailed flow simulations for vent gas, we can investigate whether areas where these gases can ignite, and also investigate the pressure buildup inside the battery pack due to vent gas generation. Now you want a predictive approach to model vent gas. As I said before, a species-based reaction mechanism is not available yet in literature, but we found that the gas generation rate was proportional to the cell heating rate. So we can directly couple gas generation rate to the established thermal runaway reaction mechanisms. So as reaction mechanisms kick in inside the battery solid, gases start to come out. So at the 2022 NASA Aerospace Battery Workshop, we showcased some of the frameworks we have developed to include thermal runaway and vent gas coupling approaches. The first framework is a solid gas coupled thermal runaway framework, where we model the solid domain and the gas domain. Thermal runaway is included inside the battery solid, and based on the reactions occurring inside the solid, you can set inflow boundary conditions for mass flow rate, for temperatures, for species distribution using a coupled UDF approach. A more accurate way to model the venting behavior within batteries is using the porous media approach, where the battery is modeled as a porous gas volume. We source the vent gas species, but also the thermal runaway energy inside this porous gas volume. And we model the temperature, pressure, and flow across this porous volume. So using this approach, you can capture better physics. Initially, for this cylindrical cell, the cap is closed. So even at lower temperatures, there's still some amount of vent gas generation. So within this closed volume, when you have vent gas generation, the pressure just builds up, and soon we can use pressure control events to burst open the cap and capture our first venting event here within 10 seconds. And then as the battery heats up, around 60 seconds, you get an actual thermal runaway event, exponential rapid heat generation, rapid gas generation, evaluate for temperature contours in 3D, pressure distribution in 3D across the porous volume, and also more accurate flow across the pressure volume, the porous volume and out of the battery. So capture better venting behavior. This model is more accurate than the previous approach, but it is also more expensive. Users can make a selection between these models and apply them to a more larger pack level simulation. In this simulation, we have done a coupled thermal runaway venting simulation where individual cells undergo thermal runaway sequentially, and they sequentially start to vent out gases. So this is a more detailed coupled venting simulation. Now these gases, when they come out, they're combust. These species are flammable, combustible, so they can ignite. So again, you can make use of SAGE detailed chemistry solver and evaluate for vent gas ignition and combustion, which is a fairly straightforward problem for Converge. In this particular problem, we seek to understand the combustion behavior inside the battery pack and outside. We showcase the flame using an isocontour for temperature, shown here in orange. We have a species distribution that comes from experiments coming out of the battery. And then we use an appropriate reaction mechanism to model vent gas combustion. And that can easily be extracted from the full C3 mechanism database available in Studio. The full C3 mechanism database contains over 3,000 distinct species with over 16,000 reactions. But you can create a reduced mechanism using the few species at hand, shown here. So looking at these simulations, you get venting within the battery pack. You get initiation due to spark event. And you see the gases only burn where the flammability conditions are ideal. And most of the burn is actually occurring outside the pack due to the fresh availability of oxygen. We make use of AMR to track species distribution and the flame propagation accurately. And this is also a CHT coupled simulation to evaluate the risk of thermal runaway due to heating up of batteries due to fire inside the battery pack. An example applied to an industrial EV battery pack from Renault, venting inside a full-size EV battery pack. Again, thermal runaway inside the solid using our calibrated reaction mechanisms, solid-to-solid thermal runaway propagation, and venting of the gases was coupled based on heat release within individual cells. For the fluid domain, we made use of high-fidelity LES simulation, and a SAGE combustion model was enabled with the GRI mechanism. And then we can study both the combustion behavior inside the pack, the predictive venting behavior out of the individual cells, and also the pressure buildup inside the pack, which can be evaluated to understand sort of stresses on this particular battery pack frame. This was the part of the previous case study I showcased, which was showcased at our Converge user conference. Now, when you start to do these vent gas simulations, the question you want to ask yourself is what exactly ignites the gases. In the previous simulations, we actually were interested in the combustion behavior inside the pack. We didn't want to predict ignition, we wanted to predict combustion behavior. So we forced the gases to ignite using a spark source. The gases will always ignite, and they are sparked at particular locations where flammability conditions are met. But the gases can also ignite if the composition is correct, there's enough oxygen, and they're also of high temperatures. So this is a self-ignition of vent gases out of an 18650 cell. Thermal runaway not only includes ejection of gases, but also ejection of solid particles, which can reach molten temperatures due to the thermal runaway heat release occurring within the solid. Those molten solid particles can act as hotspots that can ignite these gases. The solid particles are spit out into the entire domain. They can travel to areas where flammability conditions are met and ignite those gases and create flames, not just within the batteries they're coming out of, but also adjacent batteries. And all of these behaviors can be predicted using our detailed chemistry capabilities. Now, once you have a fire, you might start to look into fire mitigation strategies. People have proposed the use of phase change materials as flame retardants. When there's a flame, the phase change material melts, and from the surface, flame retardant material or gases are released that interfere with combustion chemistry. And we can utilize CONVERGE CFD as it has established surface chemistry capabilities for this particular problem, which has been used to model different catalytic surface reaction mechanisms. Again, to model combustion behavior, you want to ensure that the species that you're venting out is accurate. Oftentimes, people just have the final species after the thermal runaway event. What was the mass fractions of CO, CO2, CH4 after thermal runaway? But in reality, the species generation is dynamic. Maybe you have more oxygen in the beginning, and then later on you have more CO2 in the beginning. Again, the investigations are still new in literature, but engineers at Underwriter Laboratories Research Institute and Purdue University have identified converge capabilities and the benefits of using converge to model such problems. A reaction mechanism was proposed for vent gas generation by Zhao et al. As you can see, there are multiple gas generation reaction mechanisms that we can easily incorporate into converge. We model a solid gas coupled thermal runaway model for the venting of the 18650 battery. We use a lumped pressure approach to model pressure buildup inside the battery and mass flow rate outside the battery and heat generation inside the battery. And then using these reactions, we can dynamically evaluate for species generation. And as you can see, species generation is changing over time. The relative composition of species is changing over time, and also based on the temperature of the battery. So initially, you have a lot of O2 and C2H4 coming in, which if you look into these equations shown here by my cursor, you see that this equation represents the SEI decomposition process, which is one of the first reactions that occur during thermal runaway. So you get a lot of those corresponding gas species coming out. And then later on, you have maybe more CO, CO2, and some hydrogen coming in. So if you want to accurately predict ignition of these vent gases, you want to accurately model the dynamic evolution of these gas species. This work was presented by researchers by Mohammad Parisi from the Underwriter Labs Research Institute at our 2023 CONVERGE CFD conference. And all these presentations that I mentioned presented at our user conference can be found on our website. Once you get a full understanding of your thermal runaway and venting behavior in your simulation, you can start to incorporate more physics into your simulation and model a wide variety of complex problems. For example, when you have a battery fire, people can wish to control those battery fires or mitigate battery fires. And oftentimes they do that by using fire extinguishers that can extinguish a fire, or also spray cooling techniques to prevent thermal runaway propagation. And this can be modeled using our Lagrangian particle modeling capabilities. We have extensive spray modeling capabilities available for both liquid sprays and solid sprays. In this example, we are controlling fire using a simple water spray. More unique fire extinguishers for battery packs might involve solid-based fire extinguishers. We can also model solid-based particles using Lagrangian modeling approaches within Converge, and we can include devolatilization models within Converge, and using either constant rate or single rate kinetics, we can emit volatile components from those solid particles. These volatile components, when emitted, chemically disrupt the regular vent gas combustion reactions. And all those are included in your reaction mechanisms, which is solved by our SAGE detailed chemistry solver. Like I said before, the ejection during thermal runaway event, it's not just gases that are ejected, but the liquid electrolyte within the battery and more melted or broken off solid particulate matter can also be ejected as well. Those can be modeled in our simulations. The solid particles, you can give a particulate size distribution that can come from experiments. They are often molten temperatures or very high temperatures, so they can be included in your simulations to ignite these gases. Of course, UDF capabilities have been used along with the venting of gases. Venting of the solid particles can also include UDFs to couple it with thermal runaway reaction mechanisms inside the solid. Other simulations using solid particles can include studying the distribution of these solid particulate matter or ejecta inside your battery pack. So you can get an idea of whether the ejected solid particulate matter will cause risk to vent gas flow passage or try to block the vent gas flow passage, or maybe it can pose a risk to thermal runaway propagation because these particles are hot and can deposit to adjacent cells, as you see here. In order to model the latter effect, we have been developing a solid particle film deposition model, which includes wall heat transfer to walls and CHD solids. So as you can see in this simulation, the battery ejects out hot solid particles onto a blast plate, and these hot solid particles transfer heat to that CHD solid. In the first example, it's an aluminum solid. In the second example is deposition of solid particles on phase change material solids, which can be present inside your battery pack. Now, phase change materials have lower conductivity. So as you can see, the particles retain their heat, they act as local hotspots, and can pose a more risk to vent gas ignition during the venting process. However, the aluminum plate, maybe for the battery flame, can easily diffuse the heat out of those solid particles. Finally, venting behavior inside closed battery packs can not only change the flow behavior inside the battery, but also the structure behavior of your enclosing battery pack frame. Such detailed deformation FSI simulations can be conducted by coupling CONVERGE CFD solutions with Abaqus FEA simulations. You can model the swelling and deformation of battery pack enclosures. You can also model the deformation and swelling of battery cans or individual battery cans. Wall boundary information is exchanged between CONVERGE and Abaqus. CONVERGE provides the pressure forces to Abaqus, and Abaqus provides the displacement of the boundaries back to CONVERGE. And this, again, is a co-simulation option. Both codes are run simultaneously. As you can see, this is a scaled or enhanced deformation of an aluminum battery pack frame. Now you can run a new simulation with a different material. People seek to reduce the weight of the battery pack, so instead of using aluminum, they can use some polymers or plastics, but those might not be as structurally stable as the aluminum. So people can run these investigations and optimize on their material selection design. That concludes our presentation for today. Our presentations that we showcased at the NASA Aerospace Battery Workshop are listed here. They are available on the NASA website, but feel free to reach out to us directly and we can forward these presentations to you. Now off to Mattia for some questions if you have any, and then to conclude this webinar.